very knowledgeable colleague with whom I've had the fortune of interacting a few times. And I've learned quite a bit from him. In particular, I've learned quite a bit about the topic of his talk today, which is ion mobility, trapped ion mobility. It's a form of separating ions, and it will come as no surprise to this community that high-performance separations are very, very useful for protein analysis. They're very useful to deal with the inherent complexity and tremendous dynamic range that we have to confront. And Matt Willetts is going to tell us about an approach of accomplishing this separation in gas phase, where ions are less sticky than peptides, I believe, and there are certain advantages in speed and otherwise in doing the gas phase separation. So I look forward to hearing an overview from Matt Willetts of how this technology works and how it can benefit single-cell proteomics.
Okay, is this working? Is my microphone working? I don't like it is.
Is it on?
It is. Oh, it's off again. Turn it off. How about now? Okay, that's better. Okay, thank you, Nikolai, for the very kind introduction and the invitation to talk this morning. And thank you to everybody in the audience too. So yeah, so as Nikolai says, I'm going to sort of give you, I guess, a bit of an overview of how trapped ion mobility spectrometry can, really benefit proteomics, and of course, because of what we're talking about this next 2 days, particularly single cell proteomics. Oh, no. Okay, thank you. Okay, so I guess just a quick overview of the plan for the talk. So I'm going to talk a little bit about what exactly is trapped ion mobility spectrometry, which I guess probably a lot of the audience are already somewhat familiar with, but we'll go over it again just to talk about some of the specifics and how that works. Then we're going to talk a little bit about how the specificity of DIA when we're doing TIMS can really benefit the proteomics workflows, and again with a focus on single cell proteomics. I'll talk about what we've done with our single cell proteomic system, so our timsTOF SCP. So this is a mass spectrometer which was developed really with the idea of really doing single cell proteomics. So it has other application uses as well. Really anything where you're fundamentally sample limited, but of course single cell proteomics is really a really where this really comes into its own. And then I'll finish with just sort of where we are with single cell proteomics and the sort of numbers and results that we're getting from the system. Okay, so going back to really the beginning then, right? So probably a lot of you have seen this diagram before, but so what is going on? What's happening with trapped ion mobility, right? So obviously, I guess I should back up one step further, of course. So ion mobility is the separation of molecules in the gas phase based on their three-dimensional size, right? So not based on their mass to charge, as we know from mass spectrometry, but literally on effectively the surface area of the molecule in the gas phase. And so and of course, this is ion mobility itself has been around since almost before mass spectrometry, right? But the way we do ion mobility with TIMS is really quite different. So you see this representation of basically the system here, right? So we actually have two TIMS devices that are in series, right? So one after the other. So in the first TIMS tunnel here, we are going to first of all do an accumulation step, right? So we accumulate a packet of ions. This will be typically anything from 10 to 200 milliseconds worth of ion current. We then transfer those ions through to the second TIMS analyzer, and what we're doing here is pushing the ions into an electric field gradient, right? So you can see that represented by this slope here. So we're pushing those ions into this electric field gradient using a constant gas flow, right, which is going from left to right here on the screen. And so what happens is the ions of larger collisional cross-sectional area feel a larger push of the gas flow into the electric field, right? Whereas the smaller, more compact ions, right, so those of smaller collisional cross-section don't travel as far into the field before all the ions reach an equilibrium position where the electric field strength and the flow of the gas, it reaches this equilibrium, and the ions become trapped at different positions along here, solely based on their collisional cross-section, and I guess, and technically their charge. So the last step is to ramp down this electron. Now we've trapped them, we've separated them. So, and this gives us, quite a high resolution of ion mobility separation. So you can achieve, up to 200, 300 resolution in terms of ion mobility in this technique. It really depends on, sort of how you set the system up and the sort of throughput that you're trying to achieve. So now we've done that, we now ramp down the electric field, and the ions are then eluted, in order of their decreasing collisional cross sections into the rest of the mass spectrometer. So, this technique is actually, relatively new from my mobility perspective, but it's been around for a little while. So it was developed by my colleague Mel Park and colleagues in R&D group. And so, this is some of the I guess some of the early principles back from 2015, really showing, this fact that we have this rising edge of this electric field gradient profile here, right? So again, this is going to be acting as like a barrier to the ions. This gas flow is going to be pushing those ions on into this electric field gradient. They're then trapped, and then we elute them as I described by ramping down the electric field, and the ions eluting in order of their decreasing collisional cross section. And so it sort of ends up being the resolution that you can achieve on this actually really depends on how slowly you ramp down this electric field. So, to achieve resolutions of 200-300, then you need to be, about 200 milliseconds. But in a typical proteomics experiment, we can achieve resolutions of about 80 to 100 with this approach. So really that resolution depends on really how long the ions spend traversing this plateau here as we drop the electric field. So another way, I guess, of thinking about this is actually nicely described by our colleague Mark Ridgway in this publication, is thinking about TIMS as being like a reverse of the classic drift cell experiment, right? So rather than driving the ions through a stationary gas phase as we do in a drift cell, right, we're actually holding the ion stationary in the electric field and moving a column of gas across the ions, right? So what this means is that your analyzer itself, so this whole analyzer space can be very, very small, but the actual amount of gas we push against it means that we can achieve effective drift cell resolutions, or lengths of about 10 meters with this device. Mel, and this is ends up being the equation that really defines, the resolution of the system in terms of this voltage gradient and the time spent traversing this plateau. So that's really the basics here, right? And so when we put this on a QTOF type system in the timsTOF, right? This is where the system sits, right? So this is the part here which is doing the ion mobility. So we have just to orientate you here, we have the transfer capillary here, a deflection plate to push ions through an ion funnel. This is our TIMS analyzer, so the two TIMS analyzers as we saw before, right? So basically less than 10 centimeters here. After that, we have a multipole, quadrupole collision cell and the orthogonal acceleration into the time of flight system, right? And the timing works really well because, if we think about our typical, workflow when we're doing LCMS, obviously our HPLC takes minutes, right? HPLC peaks themselves are, anything from 3 to 10 seconds, depending on how fast the chromatography you're doing. And the TIMS process itself is on the order, as I mentioned, of about 10 to 100 milliseconds. So, and then at the end, of course, we've got the TOF, which is on a microsecond scale. So, timing-wise, it fits really nicely into the geometry of the whole process. And so, what this gives us then is, as I mentioned, this very high resolution ion mobility system and a very short device, a very small section of the mass spectrometer. So it doesn't really add anything to the size of the system. And we get significant amounts of sensitivity boosts from the space-time focusing of the ions as they're concentrated in the TIMS cell. It's a very fast process, right? So we can do, it's really very amenable to short gradients, so fast chromatography. And because we have this ion mobility separation, of course, it enables us to separate isobaric and overlapping isotope species in the system. So leaning to eventually cleaner MSMS spectra. So there are multiple, iterations of this system now, right? All the way back from 2016 when we launched the original timsTOF system, all the way through now to the timsTOF HT, where we've seen improvements in the capacity of the system, improvements in the back end digitization, improvements in software. So we've very rapidly gone through multiple generations of the technology. But of course, the system works really well. It's very, very sensitive, the whole approach, right? But what I think, if we look back a couple of years ago, still what the field was lacking is a mass spectrometer that is really able to do single cell type sensitivity, right? Without having to do other techniques such as scope, which is a very elegant way of improving IDs through carrier channel type work, but actually fundamentally improving the sensitivity of the system. And so this is what we did with the timsTOF SCP. So what you see here is a schematic of the system. And so here you see, the standard optics that I sort of just showed you before for a typical timsTOF device. So here you have the tim cell, quadrupole collision cell, and time of flight. But what we've done is to add extra optics at the front here. And so, this really represents a new ion source here, right? And with the ability to transform more ions in the beginning, right? So basically what we've done here is to increase the internal diameter of the transfer capillary here, right? So a much larger bore capillary here. So we've gone from 0.6 to 1 millimeter here. Now, of course, what this means is you sample a much larger amount of the ions, so much larger ion current. But of course, what also comes from having a larger hole in the front of your mass spectrometer is a lot more gas flow, right? And so to deal with that, you see that the ions are going to come through here, make a 90-degree turn. And then we have this extra set of higher pressure ion optics here, right? So to deal with that extra gas flow. So there's extra pumping here, a very high pressure ion funnel here to focus the ions down, and then they come down into the tim cell this way, right? So the system features, sampling more ions to begin with, but also then ions make two orthogonal turns, right? So they come in here, they make an orthogonal turn, and they come in here and make another orthogonal turn. And so this really gives us, and also a benefit in terms of removing neutrals, solvent molecules, and other things like that. So it keeps the system, even more robust. And so in the end, we see this, typically 4 to 5 times increase in ion current from this new design source here. And I'll talk a bit towards the end of here of the sort of results that we're seeing with this type design for single cells. But what I also wanted to talk about is, as well as just the mass spectrometer design, but also, how we're acquiring data, right? And so obviously, as probably most people are aware, the field is really moving, I think, a lot towards to DIA as really the main acquisition method for proteomics in general, and certainly for single cell proteomics. And so the way we do DIA on a TIMS platform and take advantage of the ion mobility separation is, as sort of we describe here. So what you see is like a top-down view of your analysis, right? So mass to charge versus mobility. And what you see is, very two distinct sets of clouds of ions, right? So singly charged, and these are singly charged ions up here. So typically our background. And this is our multiply charged ions here. So obviously the peptides of interest. And so when we're doing DIA on a regular platform, of course, this is basically using these discrete windows, which we step across the mass range, isolating and fragmenting whatever comes through those windows. And so, without the advantage of the ion mobility separation, of course, what you're isolating and fragmenting is not just the singly charged, not just the multiply charged data, but also all the background as well, which of course makes everything, more complex and more difficult to interpret in the end. So when we're doing DIA on the TIMS platform, the timsTOF SCP, so we're calling this DIA passive, our windows now also, of course, have a mobility dimension too, right? So and they're only now sitting on just the multiply charged data and not the singly charged background. So all of our isolations are much less complex and easier to interpret. So we just scan these windows across the area of interest, and so we're only going to be isolating and fragmenting and getting data from, the peaks that we're interested in. And this really does lead to a benefit in terms of simplifying the data that you're seeing, right? So this is actually a plot here from a recent publication from Florian Meyer. He was actually looking in this case at phosphoproteomics. And you can see as we go, looking at 3 different gradient times here, you can see with and without the immobility separation, you can see the number of co-isolated features, is significantly larger when you don't have immobility, right? So obviously, the more things you co-isolate, of course, the more complex a set of spectra and fragments you have to then go and deconvolute, right? So there's a real benefit to only isolating, the peaks of interest. And we've looked at this ourselves. So actually, my colleague Sebastian Wacker took a look at this and said, well, what if I take, our standard sort of in-house deeply fractionated human cell digest? So this contains, I think, about 13,000 proteins, but obviously more specifically about over 500,000 precursor ions. And if you just look at that sort of, just extract out all that data in that library, and look at what happens when you vary the immobility window size. So we go from 15 master charge to 20 to 30 to 50. What we see is that, without immobility, the number of, I guess this is the mean number of precursors that you isolate, right, is really quite high, right? And obviously, as you go wider windows, the number of co-isolation events is larger and larger again. But if we now take that same data set and look at it with the immobility taken into account now, right, you can see there's a really significant reduction in the numbers of features that are co-isolated in the system. Thank you. So you can see here, at 50 Dalton window here, we are, reducing from 132 co-isolated features to just 39. So really improving simplifying the data. And we see this, this is really important when you come to single cell analysis, right? So this is just a quick shot from a PLEX-DI experiment from some of the work that Nikolai published last year. And so you can see here, this is the multiply charge data here, right? So this is our from a single cell analysis. This is the multiply charge data. Look at all the background here, right? Because the sample itself is obviously much lower in abundance, the amount of singly charged data is relatively much more intense. And so, but if we think about the windows that we use now to isolate this, you can see that we're just focusing on the ions of interest and excluding all of this, really quite intense background. So it really does benefit you really quite a lot to do this, to avoid the stuff that we want to avoid fragmenting. Okay, so I know I'm running out of time here a little bit, but I just wanted to just touch on sort of where we are with the timsTOF SCP in terms of sensitivity and for single cell analysis. So just from a standard HeLa cell digest, we're talking about being identified with DIA passive down to 250 picograms on column, about 3,600 protein groups, and about 19,000 peptides. But moving on to an actual single cell experiment now. So what we did here was to isolate single cells using a cell-in-one system, transfer them to Evo tips using a 15 centimeter or elite column from Ion Optics, and then running this on a 40 samples a day system on the EvoSep system, and then into the SCP. And then we've actually basically binned the cells by the different diameters of the cells here. So you can see different cell sizes. And so there's a lot of thoughts about how we search this type of data, right? So what I've done here is, how do we search this? So we could take our traditional library searching result, where we take that very highly fractionated database I mentioned before, 500,000 precursors. And from that, with Spectronaut, we're seeing about 2,000 protein groups. But if we do a direct DIA approach using Spectronaut, right? So, and now rather than using this very comprehensive library, we take that data from our 5 nanogram HeLa injections. You can see we actually get quite a significant boost in IDs to about 3,000. Going a step further, and as well as including that 5 nanogram HeLa data, also using data from 8 individual single cells, right? 2 from each cell size in that case, you can see there now we're approaching about 4,000 proteins in terms of the IDs from these single HeLa cells. And then briefly, just to make sure we're not over-inferring data, this is also searching that same data set using a C. elegans library, and you can see we're identifying about 100 or so protein groups. So, it's the data is much more believable, I guess, in that respect. So then finally, looking at the data across the different cell sizes, you can see we're very, reproducibly identifying close to 4,000 protein groups with pretty good CVs. Across the whole 96-well plate of samples, we're able to identify about 4,400 protein groups, about 3,900 from 50% of the cells, and about 2,000 across all the cell systems. And what was nice is that when we sort of did some statistical analysis on this is obviously a simple PCA test here, you can see actually we see some differentiation in the smaller cell sizes compared to the large ones. And so what we think is that, looking at this data, it seems that we're seeing in the smaller cells, probably these are perhaps in G1 growth phase, right? So we're seeing a lot of RNA binding and ribosomal proteins, whereas in the what's more abundant in the larger cells is more transport and localization type proteins. So yeah, hence this assumption that maybe we're just seeing the cells in different growth phases. So I'm really running out of time, so I just wanted to, I guess, quickly conclude that hopefully you can see that using trap time ability can be really, really helpful for single cell proteomics in terms of resolving speed, resolving isotope overlap. The SCP itself really now has sensitivity where in a label-free approach we can achieve identifications of 4,000 IDs or more. So we can really do much more, I guess, deep proteomics experiments. Yeah, so I guess that I will conclude, and thank you very much for your attention.
Thank you very much, Matt. Are there questions for Matt? So I'm going to start with one while you're thinking of a question. And my question is, how much benefits do you think there will be for proteomics by further increasing the resolution of TIMS, maybe going to 1,000 slices?
Yeah, that's
it. And how feasible is that?
That's a great question. So, I think there'd be benefits from improving the resolution of time ability generally. When I'm very proud to say I have 200 resolution, that's pretty embarrassing when we think about mass spectrometry, right? When we're talking 50 to 100, 200,000 plus. So that's certainly going to be, I think improvements there will certainly help, certainly be able to further resolve, a lot of the overlapping species. It'll also create probably more sharper peaks, which will improve sensitivity. And then also I think taking more slices, as you're referring to, is absolutely would be a benefit. Absolutely. Again, isolating smaller packets of ions means that you get, the software has much less work to do in trying to deconvolute this, right? So yeah, I think all these things will particularly benefit
Great.
The approach.
Great. Sounds like an exciting space to watch. See a couple of questions.
Yeah, I have a question about TOF and Orbitrap. So not just the ion mobility. Any advantage to use a TOF compared to Orbitrap type, specifically single cell?
If you're doing TIMS, right? The TIMS is a very fast process, right? So when we ramp down the electric field, right? Every time we ramp down the electric field is a step. Those ions are sent to the mass analyzer, right? And so you need a very, very fast mass analyzer to be able to keep up with the speed, right? And so TOF gives you the ability to do 10 kilohertz, right? So very, very fast acquisition, right? Without losing resolution, right? On an Orbitrap, obviously you're going to get very high resolution, but as soon as you start to operate it in a fast manner, then you lose out, right? You're then coming to resolutions of 10,000 or below. So this approach of doing TIMS really requires a very, very fast mass analyzer at the back end for the whole process to work.
Very cool technology. And my question is on linearity and dynamic range. So are there some good studies you could point us to that have tested? Do you see 2 times more signal when you have 2 cells, 3 times more signal with 3 cells? And is there a difference plus minus the TIMS? Is there a difference in the linear dynamic range?
Okay, good question. As far as, so your first question was about when you go to multiple cells, do you see an increase? You do to a point, right? I think once you get past, Nikolai probably has a better idea of this than me, but once you get past sort of like, I don't know, 100 cells or so, then you start to see 1,000 cells, you start to see you're falling off in that respect. And then your second question was about, sorry.
I think there are 2 different things. Maybe one is the increase in intensity, and that is linear across many orders of magnitude dynamic range. The other one, maybe what Matt was explaining, is number of proteins identified.
Yeah.
And there at the beginning, we would have much steeper dependence, and eventually that levels off because we get to 10,000 proteins identified, and beyond that, without doing a second dimension of separation, is very difficult to go. And yeah, the second question was the effect of TIMS on improving that dynamic range, how TIMS help improve the dynamic range.
Yeah, so I think you benefit from doing that because you're sort of focusing only on the ions of interest, right? The latest models of the TIMS stuff also enable you to have a very high capacity of charge, right? So you can actually, I think if you could distribute the ions across the TIMS cell fairly evenly, I think the latest version of the TIMS cell, you can load about 75 million charges, excuse me, right? Which is actually really a significant amount of charge you can store in there, right? Which is compares very favorably with other analyzers like an Orbitrap, for example, where I think 1 million charges is probably as much as you can load in there. So being able to load more charge, of course, gives you more dynamic range, right, in the TIMS experiment.
Then, in a way, what I'm asking is, let's say one peptide you take and you see if that is sensitively quantified over a linear range. What you're saying is, yes, you have this incredible dynamic range where you can pick up the very low abundant peptides in addition to the very high abundant peptides, but I think it's a slightly different question.
Then I'm not sure what your question is, sorry.
We'll talk later, thank you.
Okay.
I see a question in the back.
Thanks. Fascinating stuff. I have 2 related questions. So one is, when you use this technology, what's the trade-off in terms of ion transfer efficiency? So how many extra ions don't make it through? And then the second one, you might have started answering it, is what physically is it that limits the resolution? Is it space charge effects? Is it defocusing? Is it the amount of gas that's pushing on things? Yeah.
So good. So yeah, great question. So I guess to answer your first question about uses of the ions, right? So actually, TIMS is, I didn't really talk about this too much, but the fact that we are trapping ions, right, and then moving them across and then releasing them one by one, where in parallel we're accumulating another packet of ions, our duty cycle and our use of the ions is actually really, really high, because if you think about it, we're ramping down the field, we're releasing them, not one by one, but group by group. And then the quadrupole is waiting for each one of those ion packets to elute and then to isolate and fragment. So the fact that we're storing and then eluting them over time actually means we're actually making better use of the ions than, sort of like a continuous beam instrument where we're not trapping and eluting in that sense. And then I forget your second question. Sorry. Yeah. Yeah, so I think one of the problems is the fact that when you look at the shape of an ion mobility peak, they're really broad, right? When you think of an ion rotating in space, right, it describes a certain area, but there's also some fluctuations in that, right? In terms of, because you think about it as in its three-dimensional structure, it will also flex a bit too, right? Then that flexing will make the effective width of the ion mobility peak wider, right? And so that's a problem, right? So that's very difficult to overcome, right? Because that's a natural phenomenon of the ion itself in the gas phase. So, and if you look at mobility peaks, you'll see that some more rigid structures have very, very, defined peaks, but some are much wider. So that's sort of part of the limitation. Yeah, there are certainly ways around it, but it's a challenge, certainly. Yeah. So, when you see people talking about ion mobility resolutions of 400 or 500, that's currently probably the limitation of the field at the moment.
We'll take one more very quick question from Peter Horowitz. If you can unmute yourself and ask your question, that would be great. Unmuting. Okay, so then let's move on in the interest of time because we are short of time. So thank you very much, Matt, for this presentation. We're going to move on with